In this video, we are going to break down exactly what a plug flow reactor is and how hydrogen is produced using the tubular reactor as a real-world example. A plug flow reactor is a type of continuous reactor where the fluid moves through a tube in an ordered plug-like fashion. That means every molecule spends exactly the same amount of time inside the reactor. There's no mixing in the direction of flow. It's similar to a conveyor belt where the reaction happens as it travels along the reactor and the final products come out the other end. So the concentration of reactants is the highest at the inlet and drops continuously as it travels towards the outlet. This is the key difference between a plug flow reactor and a continuous stirred reactor, which we covered in a previous video. In a continuous stirred tank reactor, mixing is instant and uniform throughout. In a plug flow reactor, the concentration varies along the length of the reactor. The tubular reactor you can see here is a shell and tube design, similar to a shell and tube heat exchanger. Methanol and vapor enter at the bottom and flow upwards through the tubes. They react over the catalyst pellets, which are packed inside the tubes and react to produce hydrogen and carbon dioxide. This catalyst lowers the activation energy and allows the reaction to proceed at a lower temperature, typically around 200 to 300 degrees Celsius, which helps to reduce the required design temperature of the reactor. This reaction is endothermic. Heat is passed in the form of steam through the shell. The reactor simultaneously provides the plug flow residence time needed for the reaction and supplies the heat energy to make it happen. Here is an important insight. For most reaction kinetics, a plug flow reactor achieves a higher conversion than a continuous stirred tank reactor of the same volume. But why? In a continuous stirred tank reactor, the entire reactor operates at the outlet concentration, which means the outlet concentration equals the internal concentration. That means the reaction rate is always at its lowest. In a plug flow reactor, the reaction starts at full inlet concentration and slows down only as the fluid travels along the reactor. So on average, the reaction rate is higher throughout, meaning more conversion for the same volume. This is exactly why tubular reactors are preferred for hydrogen production, as you want maximum conversion of methanol to hydrogen in a compact, efficient design. But what happens if you connect multiple continuous stirred tank reactors in series? Each reactor in the chain operates at its own outlet concentration, so the first CSTR runs at a higher concentration than the second, and the second runs at a higher concentration than the third. Instead of one flat concentration, you get a staircase profile stepping down towards the outlet. As you add more and more continuous stirred tank reactors in series, that staircase gets finer and finer, and in the mathematical limit, which is infinite CSTRs in series, the staircase becomes a smooth curve, which is exactly the concentration profile of a plug flow reactor. So a plug flow reactor is mathematically equivalent to an infinite number of CSTRs in series. In industry, when a tubular reactor isn't feasible, engineers can sometimes use 3 or 4 large CSTRs in series to approximate plug flow behaviour and recover most of that conversion efficiency. If you found this useful, hit like and subscribe and let me know in the comments what type of reactor should I discuss next. Thank you, and I'll see you in the next one.